Okay, so a few lines about myself. I'm a chemist. I've been dealing with chemicals as a sales manager for the last 13 years. And after, well, destiny changed my career, and I joined Coolmag 2 years ago, and as a sales manager. And I have 2 kids, and I live in Barcelona. Okay, we are our offices and our factories in Barcelona in Spain. Okay, just a few things about thermal management. Before everything is started, before the first Coolmag was born, we have a look into the business to understand your needs and what's going on. And we have to talk about, if we talk about thermal management, we have to talk about the power density, because it's affecting all of you and the whole industry. So everyone is looking, for different reasons, everyone is looking to increase the power density, to decrease the size, and that means temperature. So temperature is one of the bottlenecks for your industry to make things smaller, to make things more reliable, to do things in a different way, and also to save cost. So, and we are focused on different industries. EV, electric vehicle, is one of them. It's one of the big industries we are focused on, and especially for this industry, every time that there is a thermal event or thermal issue, has a big impact on. So I don't know, probably in Northern Europe it's different. In my country, still it's a very niche application. So there are a few electric vehicles on the market. So every time we saw on the news this kind of events, has a really bad impact into the industry. So thermal management has a lot to say in the future. Okay, another interesting thing is that once we decided to go into the electronics or thermal business, we had a look into the final devices. No? We had a look into the inverters, converters, chargers, all the things. And we found interesting things. First of all, we found that most of the materials that the industry is using are non-thermally conductive materials. So there is a lot of plastic inside the devices, some epoxies and polyurethanes with a very low thermal conductivity, PCBs, for example. And so all these materials are non-contributing at all to the thermal management of the final device. Also, this is also interesting, and it's, I mean, you can check it out on your devices. There is a lot of empty space inside a device. Empty space, I mean with air, with nothing. Sometimes it's good because you need convection, you need some fans or whatever to cool down the thing. But in other devices like OBC, for example, there are closed enclosures. Air is not contributing at all. It's affecting in a very bad way to the thermal performance, because thermal conductivity of air is almost zero. So you got a thermal problem, you're using probably not the best materials, and also you have a big volume with air that is not contributing at all. And also the third thing that we found is that most of the dissipating methods or the cooling methods are in 2 dimensions. So we talk about a plane, a cooling plate, or whatever. So you have a big volume that you're not taking profit of. So yours is something interesting. Okay, this is one of the main focus on the industry. We want to increase the efficiency. We want to increase the power density. We want to increase the thermal management and reliability also, because as you probably know, temperature is affecting to your devices, not to the devices, but to the materials. So finally, the failure rate is affected by the temperature, and we want to decrease the cost. We want to decrease the weight. We want to decrease the volumes. So it's a balance between, sometimes in different applications, it's a balance between thermal management and final performance. Okay, so this is the several questions that we found when everything started, like I said 3 years ago. Why plastics and air are still so much present in power electronics? Why most structural mechanical components are thermally isolating? That's also interesting. So sometimes we want to protect from heat, and you don't want to protect the heat. You want to take the heat out of the device. So it's a different concept. We will have a look into this later. And normally we are talking about thermal conductivity value, that has a standard value for your gap fillers, for your putting compounds, but not too much people is talking about the thermal diffusivity. That is something that we found that also has an impact. Thermal diffusivity, it's more related to the speed. So how fast can a material put the heat out? and it's also affecting to the final performance, and it's related to the chemistry of the material. Also 3D designs, I mean, they're not used normally to cool down. They're also using a 2 dimensions. And also in battery packs, we'll have a look also into this because it's another market that we are working on. If you have a look into a battery pack, you will see a lot of empty space. I don't know, it's about 20%, 30% with nothing between the cells. So there's an empty space that is not contributing at least to the thermal performance. So once upon a time, so that's where our story. So everything started, like I said, 3 years ago, in fact. And we are a chemical company. We do chemicals. We distribute chemicals in Barcelona worldwide. And we got a challenge from a power electronics industry manufacturer. Okay, these guys, they've been dealing with a choke. The temperature, they've been trying to decrease the size of the choke in a very small space, and it was for an OEC, and the temperature was crazy, was over 180 degrees, and so the material was failing for different processes. The temperature was not contributing at all, so they had a challenge. And they've been testing different materials, different chemistries. They didn't found a good combination. So the challenge was to, okay guys, you know about things, you know about fillers, you know about resins, try. So try to mix something and try to find something that could help us solving this problem, and also in a good cost, in a good way, you know. But we got some requirements. I mean, there are different chemistries available on the market, different things, a lot of different fillers, but they had to fit with these requirements, and everything that we do today has to fit with all these requirements. First of all is heat transfer, so thermal conductivity and thermal diffusivity. We're always looking to get the highest value as possible without affecting the electric properties of the material, because all the products that we are working on we talk about the electric strength between 7 to 15 kilovolts millimeter, and it's something you can play with, so you can increase thermal conductivity value a lot using graphene or using silver or using different materials, but the cost is affected and also the electric properties. So it's a balance that it's not easy to find. But we are always looking to these electrical isolation properties. Also soft materials, that's crucial. I mean, we tested a lot of things in the very beginning. Spoiler, we finally went to silicones. We tested epoxies, we tested polyurethanes, we tested acrylics, we tested, and also silicones. And we found a very interesting thing, and probably some of you had this problem in the past. If every material that is offering thermal stress, so temperature, it's expanding, so it's dilating. You know? If they don't have this ability, because they are encapsulated, for example, with a rigid resin, like epoxy or some polyurethanes, the effect, it's the opposite. So the temperature, there are different phenomena, magnetostriction, and well, different things that they are affecting the final performance, and the temperature goes up. And normally, if we're talking about magnetic material, for example, it's broken. So there is a failure. And that's because the material don't have the ability to expand, to absorb these dilatations. That's what since the very beginning, since we started testing, we decided that the material has to be soft. We can play also with it, but it has to be soft. And also because of mechanical protection. As I said, some of the applications, if we talk about the electric vehicle, for example, there are vibrations, there are a lot of things going on there. And so the material has to protect ferrites, have to protect the bobbins, have to protect different materials from these vibrations. Flame protection, all our range of products has to fit with UL94B0. It's also a challenge sometimes, but it's a must for us. And non-hazardous, this is also important because in fact, you can touch Coolmag, you can play with it, you can apply it in your laboratories, in your R&D department without any special equipment, without any danger, because we don't have any VOCs. We will have a look into this later. You don't have any chemical reaction with gases, nothing. So, and it's important because some of your industries you're not normally or working with chemicals, and some of the workers are sometimes afraid about the manipulation. Okay, so with all these requirements, we found that remember the challenge. So the challenge was to find something to decrease the temperature with all these requirements, and this is crucial for us. So As I said, we normally customers are talking about the thermal conductivity value. And thermal conductivity value is just a value on the TDS. What I mean with that? So what you are looking for, in fact, as a customer, is the final stabilization temperature, final performance. So what's the final temperature that you get when your device, when you're magnetic, when you're everything, whatever it is, it's on fully load or it's on working conditions. That's the thing. And it's not related only to thermal conductivity value, because it's related to the thermal conductivity value and thermal diffusivity, so the higher, the better, okay? But also to the chemistry of the resin. As I said, if you're using a very high conductivity value epoxy resin, your results, your final temperature will be higher than using a soft material or a silicone, for example. And also the application. And that's something I will talk later also, that it's, I will not say 50%, but it's has a high contribution on the final performance. If you get the material with the best performance that you have, and you inject it, or you pour it, or you do potting resin in a bad way, bubbles, empty spaces, whatever, it's not going to work, or it's going to work much worse than other. So that's why sometimes we really found, because we tested, that lower conductivity values, but having taking care of all this process, can have a lower stabilization temperature on the final device. Okay. And finally, we made it. So we tested a lot of things during 1 year, and this is what we got. We launched Coolmag 29 LV in March 2020, so just before the lockdown, days before the lockdown. Was a good time to do it. Okay. And we also did a special process. You can see the picture up there. We did an injection. So we did a mold, because we wanted the material to get into the holes, to get into the gaps, to get into the coils. And the final performance was awesome. So in this case, these guys that they're using Coolmag, they're using Coolmag everywhere, and the temperature dropped down over around 80 degrees. And it was crazy for these guys, because they've been able to do things smaller and to change things in the design. So then we found that, okay, guys, we have something interesting, something that could help the industry. So let's gonna make something with it. And we created Coolmag. So everything started with Cadion. You can see over there. Cadion was my company years ago. And finally, we decided to create the whole structure. That's where we created Coolmag. So I moved from Cadion to Coolmag, and we are part of PMOG Group. So PMOG is a brand, and it's a big combination of different industries based on chemical distribution and chemical manufacturing. And it was born, like I said, in March 2020. Okay, so we're sometimes. Some people think that we are kind of a startup. I would say that we are kind of spin-off, okay? Because all of us, we have good background, we have a structure within the company. So this is the PMO revenue. It's gonna be 40 this year, 40 millions, and partners everywhere, countries, and so on. And Coolmag since 2020, it's contributing to these numbers, okay? And that's what we did. So finally, we bought the factory. Everything is done in Barcelona. We do the R&D department, and our factory is in Barcelona. So it's quite interesting, because there are not too many players talking about potting resins, silicones, and most of them are from the United States, some of them from Germany, but Southern Europe, we are quite unique. So, and we do a different approach, okay? Everything that we do has to fit with all these requirements, are exactly the same, thermal conductivity, electrical isolation, and so on, okay? The applications, well, it's just a general thing, because finally, Coolmag fits everywhere. So if you have a thermal problem, doesn't matter if you do, you make the components, you do the magnetics, or you do a final power supply, or you do charging, or doesn't matter. So each application is different, but there is a place for Coolmag everywhere where it's a thermal problem, okay? This is what we got. So since 2 years ago, we've been developing 3 different families. One of them, well, it's not a family, it's only one product. It's a polyurethane product. We don't like polyurethanes too much, because also polyurethanes there's a different chemistry. Some of them are rigid. They have some labeling problems. There are new restrictions from MECA, for example, for 2023. So it's not going to be easy to work with polyurethanes. Polyurethanes work very well in big volumes and just to do a kind of mechanical protection or an adhesive properties. But talking about thermal management, we prefer silicones. So talking about silicones, we started with Coolmag 29. All of them are 2K, 2 components. Curing could be at room temperature, 24 hours, or you can increase the temperature and then you can decrease the time. Okay, and we got from one bat, I think it's better out there. So we got from Coolmag SA10 one bat. It's a very, very low viscosity product, and you get 1.1 from Coolmag 29. That's our standard. This is number 1 in terms of application. Coolmag 29 works as also has a gap filler, but it works very well in injection applications. Coolmag 32, it's exactly the same but harder. I will have some samples later. If you want to touch it, you can touch it. Because as we do everything, though normally we prefer to do kind of tailor-made solutions. I mean, changing the color, changing the hardness, changing all these properties is quite easy to us. So it's very easy because finally we have the technology and we can play with it. So these are general things that they perform very well. But if you have any specific requests, we can do it. And Coolmag 32 was there was a customer that they wanted to replace the enclosure. Sorry for that. And it was they wanted a hard product to be able to protect the device. That's why we made the Coolmag 32. Coolmag SA30, it's a brand new. It's a 3 bats product. It's a high thermal conductivity value, taking care of the other properties, and it's under industrial trial right now, so it's going to be launched in the next weeks. And out there was the Coolmag Plus. I will talk about this later. Coolmag Plus is a different family. So as I said, when we started looking into the industry, we realized that plastics are very, are a common material that you're using on your daily basis. So we decided to do a thermally conductive plastic. And in this case, we are starting with a polyamide. That's what we do. We're trying to create new plastic materials with thermally conductive properties. Okay. And the main applications, and there are some examples. Well, as I said, wherever there's a thermal problem, potentially fits. I mean, you have to study case by case. First of all is power electronics in general, auto, no auto. So, and we are talking about even the magnetic or the magnetic or the device. So we sell and we provide Coolmag to players like your company, like Charlotte, okay, and also to tier 1 and tier 2. And OEMs, it's a different story, but some of them, they're getting into the business, the potting business. So you can apply it both in the company or in the final device, okay. Also, battery protection. It's also interesting. There is a video, I don't know if it's working, doesn't matter. Battery protection is also a good market for us. We are trying to get in, as battery protection has 3 different approach. First of all, they need extreme fire protection. So, because as I said, every time there is a thermal runaway, every time that a Tesla burns out, it's a disaster. So these guys are looking to the best protection. And there's a video out there, you can check our YouTube channel. And we take a battery, a pouch battery, and we burn it out mainly. And it was nothing happened. Temperature without Coolmag was about 1,000, and the battery exploded. And doing a kind of enclosure with Coolmag, the temperature raised 600 degrees, something like that. And the battery is still working today. It was no fire, it was nothing. So that made us think about, for example, if you talk about the electric battery pack, if you got a thermal event in some of the cells, the battery could potentially still working, because the material will protect the whole thing. And also it protects from the cooling thing, because you probably know batteries below 0 degrees, they're not charging a lot. So some of the customers are putting some heaters inside the material, so the heat transfer is faster and it's much more efficient than using air. Okay. Well, no, it's on the other side. But don't worry. It's okay. No, don't worry. And this is just an example. This is quite new because it's Tesla. I'm sure that this is not Coolmag. Okay, this is not Coolmag. It's a product from a competitor, but this is just a good example of how the approach is changing. Same company, years ago, you got the battery pack, and you can see the cooling system that you have. Air inside within the cells, a lot of air. So the thermal approach was probably not the best. This is the last Tesla battery. You can check Munro YouTube channel. This is crazy. These guys, American company, they take batteries, they take full cars, and they do crazy things to these things. They prepare a report, and you can buy it. So this is a new Tesla battery full of potting resin. Okay, full. You cannot repair it. So they're 100% sure that it's gonna still, probably because the thermal management of the battery is much better. So you can increase the power density of the battery. If there will not be any fire event, and you cannot open it. So this is what you get. So it's just for your information how the same company can change these things. We are under testing at the moment. We're on the next week. We will have the report. As you say in the previous picture, we prepared simulation of cylindric cells, and next week we will have the results, because obviously you're adding weight. Talking about potting resins of silicones, normally the density is about at least 1.7 to 2 grams, so centimeter, so square centimeter. So it's very high density, so you're adding weight to the battery. But on the other hand, it seems like the thermal management of the battery it's worth it to put all these things inside. And also, our chargers in general, we are focused on both off-board and on-board, DC off-board chargers, for example. For sure. And onboard chargers, it's crazy. So it's an industry that everyone is going there. Each electric car or hybrid car has to have an onboard charger, and the power density of the chargers is changing really fast. So in the very beginning, 2 years ago, we had this customer making 7 kilowatts onboard charger. These guys just took Coolmag 29, they put it inside, and they've been able to double the power concentration without any change on the design. Just because there was an aluminum enclosure with a lot of air inside, and what you get, it's a thermal path from the hotspot to the enclosure and then to the active cooling. Because we always recommend, don't forget that Coolmag is not cooling. Coolmag is just getting it's like a thermal path. So you need an extra. Sometimes you need, sometimes not, but we always recommend to have an active method, okay, to help. In this case, it's also crucial because onboard chargers, as a battery packs, they're sealed, they're closed, so you cannot use convection to cool down. So and you need a very, very efficient. Right now, everyone is working on 11 and 22 kilovolts. So it's the power density is increasing a lot, because finally, as users, we've been talking about this topic. What we want is exactly the same performance that we have right now. So I want my car to charge it in minutes, and I want the battery to last 1,000 kilometers. This is what I get. This is what I want. So, and this is a lot of things to say in that sense. Okay. And you can use both. We have a very low viscosity product, Coolmag SA10, only one bat. It performs very well if the power concentration is not big, let me say. And then we got Coolmag 29. It's a medium high viscosity. Also, you can play with it to get better thermal performance. Okay. And this is the Coolmag Plus. As I said, this is a different thing. Maybe some of you could find it interesting. It will be a launch in weeks, really, because we have the product developed and we have the results, and this goes for a different thing. So I have also some samples. This is a compound, so you have to inject it. Okay, this is kind of pellet, and your injector have to inject to make different things, coil bobbins or whatever you want. Okay. And this is also very, very important for us. So when we really started 2 years ago, we started sending you samples to the customers, to the market, potting resins, and it was a mess. It was a mess because most of you, even the bigger companies, even the higher technology, they don't know how to manage with chemicals. So we've seen crazy things. I mean, it looks very easy. You have two components. You mix both, you stir it, and you put it inside. No way. And Norbert knows what I'm talking about. I mean, thermal management it's not a, I mean, it's a need. So everyone is talking about this topic, but there's not a lot of information. So, and we decided, okay, we have to do a different approach. We have to change our business model. We have to do the injection, not in the industrial part. But now what we do, okay, you get a problem. You get a, whatever it is, magnetic, an OBC, a battery pack, whatever it is. You can send the device to us, to our laboratories. We do the injection, because we will talk about this. We recommend, if it's possible, to do an injection. Injection, what it means? You have an enclosure. You can make a plastic enclosure, or you can make just a plastic top, or whatever it is, to inject, to be able to inject with a gun, with a pneumatic gun, or with a machine, like you see over there. Why? Because we're talking about very, very low pressure, 1 bar, 2 bar, so it's nothing. But you replace the air, and then the material goes in a deep way. And sometimes what we found from our customers is that talking about temperature, differences between just putting the thing here like this and injecting could be 20%. So it's a lot. It's a lot. And up to you. Sometimes you have an open design, open enclosure, and you have to inject it. Sometimes you can play with both methods. But this is what we do. Okay, we take care of the whole thing. You send us the device, or at least you send us the step file and whatever it is. We do the molding. We do the plastic top, whatever is needed. And we can send it back to you, or we can inject it and send it back to you. And then after you, or you can put some thermocouples or whatever you want. You test it, okay, and you say, okay, it's approved. Okay, I want to start production or whatever it is. We can support you also with it. So we have our own machines, or potting machines, that we offer as a renting service. So as long as you need to apply Coolmag on your industrial process, we can leave our machine to you. We can adjust it and play with it. Or we can teach you, because some of the customers are using epoxy resins, are using polyurethanes, and even silicones. So we can help you adjust the industrialization during the industrialization process, in order to be sure that the product it's going to be okay. Because as I said in the previous slides, it's not only thermal conductivity, it's not only chemistry, but the application, it's a lot of things, has a lot to say in this process. And that's it. Well, this is a video. You can also check our website. This is not a problem. This is one of our customers, Premo from Spain. And this is just an example of how you apply Coolmag. So it's just in the lab. This is small scale. This is a pneumatic gun. There is a cartridge with both components, mixing tip, and there is a plastic mold over there. And there are 1, 2, 3, 4 chokes, if I'm not wrong. You just close the thing and inject the material there, and that's it. Because the material, we can play with the viscosity. You can even put it on production. So put it on a box, and you can send it back to your customer, wherever it is, and it will be curing during the process, because it's not gonna fall down. It's gonna stay there. Okay. Some examples of what we do, of the injection process that we do for our customers. For example, in the first picture, you can see just a pouring or potting system. This is Coolmag SA10. So this is an overcharger, and the customer just put the whole thing there, and that's it. It's a quite easy one. The other ones, you can see the molds and how we inject the thing. Probably if you're thinking about industrialization process, you will think, oh, it's too complicated. No, it's not, because you can you can do big molds with hundreds of different devices, and you can inject it with a bigger machine, and it takes seconds. Difference between casting or puring or injecting, it's time, it's cost also, and it's cleaner. So it takes a really, really short time to do that. Okay, and that's it. That's it. Okay. I hope you enjoyed my presentation. It's just a general one. So after that, I think this afternoon we can have a talk up there. And if you have any question, any technical thing, just let me know, and it will be a pleasure to help you. Okay. Thank you so much.
Thank you, Javier, for a nice presentation. Some questions from the audience?
You talked about the difference between conductivity and diffusivity. Are you going to report that in the data sheets?
Diffusivity?
Yeah.
Yes. Yes.
Okay.
I mean, on the request.
Okay. That's
Because
good.
I mean, it's not a secret anymore, but I think we want to keep this value for us or for the customers, in fact.
Yeah,
So
yeah,
we can, yeah. And we also have special reports comparing different materials and different. So if a customer wants to know this information under an NDA or something like that, we can share it without any problem. Yes.
Okay.
And what is the curing time of this product?
You can curing time, open time. So once you mix both components, it takes, I would say, depending on probably in Spain, the time is shorter because we're, but from 40 minutes, something like that. I mean, the product will be starting curing, so it will be kind of film on the surface, and then you can leave it under room temperature, 25 degrees. It will take to get fully cured 24 hours, probably less than that. But if we have a big volume, 24 hours. If you increase the temperature, you can go through, I don't know, 100, 120. It will take 40 minutes to get fully cured. So you can play with it, yes.
And I like the passion you have for your products.
Yes, thank you. Great.
Thanks, Norbert.
I have a practical question. When are you usually being called by the customer? Are you being called when they have an issue, like when you showed on the pictures when a Tesla burns out, or when the design process has been going on for months, sometimes even years, the final product is in the market? Is that when you get the call? Or then in relation to the customer sitting here, should the call be done at the early design stage? But then the question is, how is your experience with openness of customers to implicate you and get you in the team to think with them at the design phase?
That's a very good question. Well, two things, different things. Normally, I would say where they are in a hurry. So why? Because we are quite new. So if we talk about big companies, like, well, there, you know, when you know which companies I'm talking about. All these guys, they don't know us. So and we are getting into a huge business. So there is a big responsibility on the performance, so they have to trust you. And we are just on the beginning of this relationship. So normally, right now at the moment, when they're in a hurry, probably they came to us, or they come to us, they ask some questions, and they say, okay, I have 2 weeks to get some results. I need your help. And that's because they're in a hurry, because they need to increase the OBC power density by twice, and they have to finish the project in 2 weeks, something like that. This is also it happens a lot. And then they don't care about you. So they don't care about if you're new, if you don't have any experience, if you don't have nothing. So I need your help. And the more and more the world is opening. So we're investing in marketing. We're doing some noise with people like you, with your help. So the more and more the customers are just learning about us and about thermal management, because probably 4 or 5 years ago, the problem was different. And on the last, talking about the electric vehicle, the power, so the thermal management, it's, as I said, one of the bottlenecks. So I've seen, during the last 2 years, I've seen, let me say, the thermal management concern, it's increased a lot. It's been increasing a lot for the last months. So right now, sorry, I forgot it. It was a good question. The thing that we are trying to get into the industry is that point that using Coolmag or different materials, but especially Coolmag, before or during the design process, will make your final device much better. So people some of our customers that have adopted Coolmag in their engineering departments, they're making things that without Coolmag, they didn't work. So they don't work. So they cannot do these things if they don't put Coolmag. So they just consider Coolmag as an aluminum closure, as a magnetic part. So it's a component of the device. They design from the very beginning, thinking about our thermal compound. And this is something that we are working on with all the technical departments to think about so because normally what's the process? What has been the process for the last years? Okay, I do everything, and then I have a thermal problem. I put something in it, and that's it. I fix it. It's not working like that. So, or not at this moment. You need to take in consideration different things, materials, potting conditions, even the final application. Because, for example, you have it's quite common. If you have a aluminum enclosure, and you do it in a certain way, you're not going to be able to inject the material in the final phase. So just changing slightly the design from the very beginning, it will be much easier the final potting application, because you can do a top coat or whatever it is. So both, we're there in a hurry, and this is something that we want to change. We want to be, since the very beginning, since the design stage, and it's something we have to work, and we have to fight against other players on the market. So we think that we do things in a different way. I don't know if it's because we came from other industries. I don't know, but I think that could be very interesting. Yeah, good question, very good question. Thank you.
Thank you, and indeed it follows a little bit the guidelines that we want to give also today, as Tom already presented, and we will show on later. It's not only a thermal challenge, but also sometimes a timing challenge. So
yeah.
It's always a combination. Any other questions?
You showed a choke in the beginning of the presentation, and so you used potting with Coolmag, and everything around the source of the heat, so everything except for the windings got colder.
Yes, exactly.
But what about the temperature of the winding itself?
I don't know, probably we have the numbers, because there were some thermocouples inside, so I cannot tell you exactly, because well, I don't have the numbers up there, but it should be probably the ambient temperature was dropped down about 80 degrees, so was finally, I think, was 100, so probably dropped down around 80, something like that. What we know about the magnetics, talking about magnetics, is that using Coolmag 29, you can drop down. It's a medium. It's a medium value around 40-50 degrees, something like that, for depending on the pore density. But we talk about if you're going to 150, you will get 100, something like that. Doing this injection process, if you do it like casting, or this is the temperature will be a little bit higher. Yes, I can give you the numbers as well. We then made a report also with specific numbers of the choke. There is under NDA, but I think that we can share with you if you want it, and you will find every stage that we did, because there was a final design. So there were some interactions, changing the designs with the potting to get the final performance.
Sorry.
How does Coolmag age?
The company?
No, the product. The product. I can imagine that it works. I just made it, but how does it work in 4 or 5 years' time? Is it still performing the same?
Yeah, it looks. I mean, we did a lot of different testing in terms of the.
You are 2 years old.
I'm 2 years old. Yeah, I know. I mean, we have the experience that we have at the moment. I mean, on the paper, you know that there are some testing, certificate testing, especially for automotive. That they are testing the materials on different extreme conditions. Let me say, some of them are testing the material for 1 month, 200 degrees. Others are doing kind of temperature changing phases, humidity test. There's a lot of different testing. For sure, we don't know what's going on in 20 years. But I mean, we have a very good technical background in terms of the ISO or norms. So, and if we fail these certifications, we hope that everything is going to be okay in the next 20 years. There's something that once you get into the electric vehicle business, there's something that the customers they want to be sure, and they make you be sure, singing some papers to protect the final performance in the last years. But yes, I mean, we don't have this real, let me say, this real performance. It's something that we have to think that it's going to be right.
You could simulate it, basically.
Yeah, we do some simulation. Yes, also. Yeah, we have some customers that we are putting our values inside the simulation. So. Yeah.
Thanks. Maybe a question from my side also, because you talked about silicones and of course silicones and electronic applications is not always an ideal match with some processes which can happen and have a bad influence. Is that something that you encountered, or how? What can you tell us about that?
Yeah, because I mean, some of you probably, if you think about silicons, you will say, no way. Because, and that's why, well, historically, there are two kind of silicons. I mean, we talk about addition silicons and condensation silicons. Condensation silicons is that probably you know, if you're using at your house, for example, they smell like aseptic, so their chemical reaction is different. So we are using addition silicons, so you got two components, you mix it up, and that's it. You got a chemical reaction, there's no gas, no VOCs. In fact, we are one of the, there are not too much people having this, where regarding to Coolmag 29 LV, we got the NASA outgassing certification. That is a very, very difficult one to get, and especially for silicons. So there's no humidity, any VOCs, any nothing inside the material. So you can put it in the closed enclosures. So as there is no reaction, as I said, with the condensation silicons, the old technology, there was a chemical reaction. There was some gas things, and they were low molecular weight silicons. And these low molecular weight silicons, if we talk about relays, for example, when they're acting, because of the temperature of the process, let me say the polymer part of the silicon blows out, so disappears, and then you get silica. And silica was damaging the release. So we have both. Some of the customers they didn't want to, or it was difficult to get into the business because of the silicon chemistry, because of that, because of the VOCs and gas manipulation, and because of this process. That is not happening with our products and our chemistry. That's a good question. Yeah.
Thanks for that. You have remaining questions? Then, if there are no questions, I think it's almost 12. I want to thank again Javier for your speech, presentation, and also Stefan again. And we do have a small gift for you both. So, Yves, if you can take it in the room, please. Typical Belgian present which you can take along. I think you can already imagine what it could be. So we appreciate your effort of coming over.
Okay, thank you so much. We appreciate it. This is not chocolate. This is something better, right?
It's
Thank you very much.